on your t-shirts, arrows.
Full t-shirts of one of Ruth's first papers.
To celebrate my first paper.
You made the t-shirt.
When he was super young.
2007. It's the cover of one of the edition of Harvard Thinkers separate paper. Two thermostats interacting.
Thermostats.
We tried to extract her from Russia.
That's stuff I know about.
The grandmother.
Congratulations, the first talk you gave was such a success that you wanted to my experience.
That's what they parachute, everything in place.
The first talk in English was a draw.
Exactly.
Oh, go on.
Well, yeah, in that case, I'm happy to provide some light for you.
Sweet people by the end of the week.
40 minutes of talk. I had to speak at it, so.
No, no.
I was talking very quickly. And the first PowerPoint we have already.
All right, good.
Look out. I see the title is already forgotten on your face.
I'm so glad.
Like that as
I hope so too. I guess you'll find out.
All right, let's get started for today. Before introducing our speaker, I wanted to remind you of the events this coming week. On Friday, Heather Douglas will be giving a talk on rethinking public funding for science. We're looking forward to that talk. It'll be really interesting. On Tuesday, Leonardo, who is right there, will be talking about life and how to operationalize definition, how to provide an operational definition of life. If the title hasn't changed, is that correct?
Yeah, it wasn't changed.
And on Friday next week, it's I believe the last annual lecture series event of the year, and we are delighted to invite Carol Lee. However, she will not be in person here with us. The talk will be on Zoom. It's going to be about institutional racism in science, and she will be talking about her work on NIH peer review. She's been doing a lot of empirical work on the matter. It's an interesting and somewhat provocative talk, so I'm looking forward to that talk. If you want to come to Carol's talk, you should go to the center's website, find the calendar, and register for the event, and you get a Zoom invitation to join us. Today, it's my great pleasure to introduce Ruth Kastner, who is with us today. Ruth got her PhD from University of Maryland. She's been a research associate there for a long time. She has published extremely widely in the philosophy of physics, mostly with respect to the foundation of quantum mechanics. And so I won't review the whole CV, but I will just mention her most recent book, just only because the title is really nice, Adventures in Quantum Land, Exploring Our Unseen Reality, published now 3 years ago. And before that, there was Understanding Our Unseen Reality. Not things are not seen. We are going to, hopefully the slides will be seeable, solving quantum riddles. And Ruth has been a fellow with us at the Center for the whole semester, and we've been really enjoying her presence. Ruth, the floor is yours.
Thank you very much, Edward. Can everybody hear me all right? Okay, so well, the title of my talk is Curing Several Diseases of Physics with One Simple Remedy. And I like the remedy. I hope maybe you will too. It's somewhat radical. Okay, so let's see. Am I going the wrong way to the next slide? Okay, so here's the abstract. So modern, as I'm sure you all know, modern physics presents us with a number of stubborn problems and challenges, chief among them the measurement problem of quantum theory. I suggest that many of these problems arise from an underlying unduly classical metaphysical picture of entities and processes that needs to be recognized as optional and critically reevaluated. Once the inappropriately classical metaphysical picture is renounced in favor of a more appropriate one, the problems drop away and a fruitful way forward is revealed. So I'm hoping to, give, if not convince you of that, at least give you something to think about. So I'd like to start off with a quote from Roger Penrose, who said that, expressed the view that in order to understand quantum non-locality, we need some sort of a radically new theory. So he's thinking in terms of a big revision of the way we approach quantum theory. And in his mind, at that time when he wrote this in 1997, he said that he thought it would have to be something which has a completely different conceptual framework. In this picture, quantum non-locality would be built into the theory. So my claim here, what I'd like to try to persuade you of, is that in fact, quantum theory is a basic formalism is fine. But what we need, the completely different conceptual framework that we need, is primarily a different picture of field propagation and a revision of the body of conceptual notions that uphold that current picture and make it seem as though it's necessary and unavoidable and the only way to do things. So a slight diversion, I'm going to recall an episode in the health sphere, the high fructose corn syrup problems, hopefully will become relevant to you as we proceed. At some point with this problem consists of this history that at some point soft drink manufacturers started using high fructose corn syrup. People started developing illnesses, various kinds of strange illnesses. After some research, the physician community, the medical community realized that this stuff was really bad for you, and getting rid of it, replacing it with a healthier diet, solved the problem for people who did that. So again, the diagnosis was high fructose corn syrup poisoning to cure a healthier diet. So I'm going to come back to that later, but that's just kind of an example of how a habitual kind of behavior might be doing something bad and you didn't realize it. Okay. So briefly, reviewing the perplexities of quantum theory, I'm sure that you're all, most of you in the field or interested who have been following the field are all familiar with these, but we'll briefly review them. So of course, the measurement problem, which is exemplified by Schrodinger's cat, who is supposedly in a superposition of alive and dead. We also have apparent energy divergences in quantum field theories that just, besides the fact that they seem problematic in their own right, they're also inconsistent with certain developments such as the cosmological constant, which we know has to be small. And if you try to explain that with the vacuum energy, it's just way too huge. So that's a problem. And then, of course, the apparent incompatibility of quantum theory with general relativity because of its non-locality, and the general inability to define a gravitational field for quantum systems, since obviously they're in superpositions of paths and so on. So there's no well-defined metric there. But I'm going to briefly just kind of turn some attention to what I feel is a slide into, for the most part, forms of uncritical instrumentalism about quantum theory that has been a response to these kinds of problems. I'm just going to go through this very quickly. There's kind of a lot on this slide, and I don't want to dwell on this point, but basically what I'm going to argue for is realism about quantum theory, that it's perfectly valid to interpret quantum theory in a realist way, and by which I mean as referring to something in the world. So this is, you may have a different view, but what I feel that I'm seeing in the literature are various forms of instrumentalism that seem to have kind of crept in without a lot of discussion. What I'm calling naked instrumentalism is when you read these kinds of statements about quantum theory is a calculus of probabilities for obtaining measurement results, and that they define it that way. And then what I want to call de facto instrumentalism, simply because the way the theory is being discussed in the paper, it's assumed that any application of the theory is always relative to some agent or pointer or various objects or entities that need to apply it. In other words, that once again, it's a tool to be applied. And it's often demanded that such a specification be provided even as a condition for discussing measurement results. So in fact, people will say, well, you can't say that a result happened unless you tell me for whom this agent, for which agent a measurement occurred. And so again, that's a form of instrumentalism, because it's assumed that you can't even talk about a result unless it's observer dependent in some way, or being obtained through the use of a tool. And then we have recent paradoxes that are coming out of Wigner's friend type scenarios, where we actually get a situation in which the theory for an envisioned kind of propagation or evolution of a system, you get inconsistency. So you get one system coming up with a certain result or prediction, and another system coming up with a result or prediction that really conflicts with the other one, and they simply cannot obtain together. And so a lot of responses to these kinds of situations are that alarm bells go off, and exemplified by that, actually. Okay, so the question of certain things that I consider tactics of kind of dodging the message that the theory you're using is not working in some way. You can question whether a degree of freedom can count as an agent applying the theory. Consider whether an agent's memory might be erased so that you wouldn't get the conflict. The denying that incompatible results can be combined, even when such results are already yielded by the theory. In other words, there's arguments in the literature when you have mutually conflicting results that could even result in empirical inconsistencies. There's an argument that presented that, well, you simply cannot combine those, as if quantum theory hasn't just given them both to you, so you don't have to do anything, they're just there, but given to you by the theory. But anyway, these are, I think, different forms of instrumentalism. So I'm going to argue that we don't really need to do that. And as a way of getting at just further kind of getting a view on what the dysfunction is, I think, is that we're often conflating two distinct senses of realism. So we can have realism about a theory in which we're simply saying a theory's elements refer to entities and or processes in the world. And then there's a different usage of realism, local realism, with the little LR, just kind of tag that with a superscript, which is a metaphysical claim that reality is classically local and determinate. Well, we all know that this is pretty much not true, that quantum theory is almost certainly telling us that you must let go of local realism. However, what we've seen in response to that, I think, are two main kinds of responses. What I call A, which is attempting to salvage at least some aspects of realism, for example, interpretations that claim to be able to save locality, or again, B, towards instrumentalism about quantum theory, which I've briefly described. So my view is that both of these responses are driven by reluctance to let go of inappropriately classical metaphysical presumptions. So I'm going to argue that we shouldn't abandon the idea that quantum theory describes the world. It's just that what it describes is not characterized by a metaphysics of local realism. So just very briefly, I have a lot of slides, so I'm going to just very briefly kind of try to zip through some of these. But saving locality, in my view, that this may be a bit harsh, but I feel like that's maybe the same kind of mistake as trying to save the geocentric model. Arguably, locality just simply does not apply to the domain described by quantum theory. So we need to let go of that. And then again, retreating from realism about quantum theory. And here I'd like to remind us of this very insightful statement by the late Ernest McMullen, who reminded us that imaginability must not be made the test for ontology. The realist claim is that the scientist is discovering the structures of the world. It is not required, in addition, that these structures be imaginable in the categories of the macro world. So that's really an important insight. And again, one that Bohr, didn't have at his disposal, because as we know, Bohr really took the opposite view that that if your domain of your theory, if you can't describe it in classical terms, then it doesn't exist. And he rejected that sort of approach. So in contrast to Bohr, I'd like to keep what McMullen said in mind and suggest that this is the way to go. Okay. So of course, the results we get from quantum theory are contextual. Okay, we know that. Heisenberg uncertainty principle. But I'd like to direct our attention to asking, what does this say about the world? Okay, so the challenges in specifying what counts as a context in the world without the kind of retreat into observers, agents, and so on that are really kind of primitive concepts and used as a way to turn to instrumentalism. So just want to remind myself of how I can keep myself on track. Okay. Yeah, I can see I'm okay. I can see I'm going to go over, try to zoom through this. Okay. So back to our high fructose corn syrup situation. So I think we have a parallel here. So based on the realism notion that we all have been marinating in for our entire lives and entire, recent to modern human history, perhaps, we assume that fields must propagate locally and unilaterally, unilateral local field propagation. Theories started developing illnesses. We had the quantum measurement problem. We have quantum field theory infinities and inconsistencies. This is pointed to by Hodge's theorem. We've got an incompatibility of quantum theory with general relativity. So what I'm suggesting is that we eliminate the unilateral local field propagation view and replace it with a different theory of fields, the way fields behave, which is the direct action theory. And in the remainder of the talk, I'm going to briefly describe that. It's going to be, sorry, the cartoon version. So just skimming over the surface, but for those of you who are interested in quantitative details, I'm happy to provide references for that. So the diagnosis is unilateral local field propagation poisoning. And the cure I propose is the direct action theory of fields. So in other words, Sabine Hassenfelder mentioned this in a recent talk she gave. Deeply held philosophical convictions are getting in the way of science. So I'm going to briefly review now those convictions, the sort of traditional Western metaphysical view, and that these are the ones that I think need to be unearthed. Most of us don't even realize we have them, but I'm going to try to bring them out and suggest we need to question them. So here, the sort of tennis, what I call the tennis serve picture. This is the unilateral aspect to field propagation. So nothing happens unless a single player hits the ball. Then everything happens. The ball just does what it needs to do. It pursues a trajectory as an independent object. And of course, when you lay this out, you kind of think, well, yeah, of course, that's obvious. That's the way things work, right? Well, maybe not necessarily. Here's another feature of this unilateral local field propagation, the locality. So in quantum field theory, where we represent a field as a set of operators associated with each space-time point, where they very carefully carry, the bucket brigade sort of picture of energy from one space-time point to another. At the speed of light, nothing can go too fast. So that's the metaphysics behind that approach. So let's just kind of consider now, in opposition, the Eastern concept of yin and yang. I'm sure you've all heard of this. We have in Asian and Eastern cultures, we have this concept of sort of balanced processes, the yang type processes and the yin type processes. And these are just some of the modes that are associated with each of these kinds of these concepts. So yang has the initiating, creating, offering, emitting kind of role. And yin has the responding, destroying, accepting, absorbing kind of role. Okay, so in Western metaphysics, this is what we have. Okay, we have all yang. We don't know about yin. We simply describe, our theories presuppose that yang is all there is. That's the only kind of process in the world. And that's where we are. Okay. And that underlies the unilateral local field propagation picture. So what we get, arguably, is this kind of reminds me of this famous koan in Zen Buddhism, that what is the sound of one hand clapping? Well, you don't get anything because this is yang only. You get nothing. That's one way of answering it. I'm sure that the Zen master probably had something much more subtle in mind, but for current purposes, we can kind of see this as a way of understanding the measurement problem, that you're just getting unilateral propagation. Things are going out. You're not getting anything happening. So what I'm arguing is that in order to make progress, we need to relinquish this unilateral yang only picture. And we need to relinquish our usual demand for locality at all levels of nature. So recalling Penrose's comment that we are going to need something that has a completely different conceptual framework in which non-locality would be built into the theory. So this is what you get in the direct action theory of fields. The non-locality is built right into it. And so I'm going to argue that that is the theory we need. And if we use it, we can keep the basic quantum formalism and resolve outstanding problems. So in this regard, I'd like to recall a wonderful quote from Nicholas Rescher, who was here earlier in the semester and discussed, I think he was discussing futurism and how that was a branch of investigation. It turned out to just kind of be not something fruitful in the long run. And he observed that the tree of knowledge grows new branches, but also loses old ones. So I think this is a good way of looking at it. And of course, there's nothing wrong with what scientists have been doing. They've been exploring an avenue that seemed natural. But I'd like to suggest that we acknowledge that it's no longer fruitful and clip that off and add some fertilizer in the form of the direct action theory. Okay, so what is this direct action theory? Well, very quickly, an early classical version of the direct action theory was called the absorber theory of radiation. And there were pioneers prior to this, Stuckelberg, I believe, and some of you may know others, who were pioneering this theory. But Wheeler and Feynman were the ones who, in the 1940s, really formalized it and presented it and advocated it for a while. Then they turned away from it for various reasons that I discuss in my book. I have a second edition of my Cambridge book that was published in 2012 that'll be coming out in June of this year. And I go into some detail about, the history behind that and why Wheeler and Feynman decided not to pursue that, but basically there was nothing really wrong with it technically. And in the 1970s, Paul Davies developed a semi-classical form of that theory. It has some quantum features, but it still has some semi-classical features. Kramer made use of this theory in 1986 to develop what he called the transactional interpretation. And that was basically a non-relativistic form of the direct action theory that he applied to quantum theory. And then I've been developing that theory into the relativistic domain and and my work has basically used the Davies theory as a starting point, but reinterpreted certain aspects of the theory so that it is now fully quantum rather than being semi-classical. So the basic picture is that in this theory, emitters and absorbers both generate time symmetric fields. And it is the absorber's response to the emitted field that actually generates a non-unitary interaction that transfers energy that we can identify with the measurement transition. So just briefly, in the fully quantum relativistic form of this theory, we actually have two levels. We have two kinds of processes. We have a unitary process that consists of the direct time symmetric connection between sources of the field. And in that case, there's no emitter-absorber relationship. They're simply, they're not emitting or absorbing energy, but they're conveying force. And then the second kind of process is energy-based and it's non-unitary. This is the so-called absorber response, when you get absorber response. But the term absorber response is really not fully accurate at the relativistic level, but I use it simply so, you know, as a way of getting to the concept. At the non-relativistic level, it's absorber response. So again, this is the basic interaction. We just have two charged particles interacting in a force-based way. There's no energy being transferred. And this is a virtual photon, which I probably should have pictured as a dashed line instead of the wiggly line, because it's really an off-shell virtual photon. There's no energy transfer there. And then this second kind of interaction, which takes place upon when you have a well-defined emitter and absorber relationship. And in that case, the absorber is responding with a kind of a time symmetric field that operates in this way, where you can see that if the solid lines are the retarded field propagating in the future direction, and the dashed lines represent the advanced field, which is propagating in the past direction, then you get this reinforcement between the emitter and absorber, and you get cancellation everywhere else, so that this is how you get the real energy that is transferred. And for fans of quantum field theory, this is a very, very quick little technical detail that actually shows in a very elegant way. I believe this is from Berestitsky, and I should have put the reference in, but for those of you who want it, I can get that for you. But the scattering matrix, for the most general form of the scattering matrix for the quantum electrodynamics, actually looks like this. So it has a term that expresses direct interactions between currents, the Feynman propagator, and then it has a factor that deals with so-called external photons, if there are sort of photons in the field in the usual way. Well, the direct action theory just consists of saying, okay, there is no real mechanical system called the field. That's not, in other words, if you recall the bucket brigade operators, they're not really there. Okay, so they're not really there, and we don't really have unsourced photons. So we simply set that to 0. This factor goes to 1. And then all we're left is this direct connection between currents. So in this expression, the real part of the Feynman propagator is the time symmetric component that describes virtual off-shell photons. This is the force only connection. And then the imaginary part here, as the way the propagator is defined, corresponds to the absorber response, which gives you your radiation reaction that kind of allows you to say that an accelerating charge radiates real energy. And again, I have some further specifics in a preprint that contains material from my second edition, and for if you want to get more details on that. So the quantum direct action theory is what we would consider the transactional interpretation, but TI is really a different formulation of quantum theory because it's based on a different theory of field propagation. You know, I used to say, oh, it's just an interpretation, but in fact, it really is a different theory, although it is empirically equivalent to the standard theory at the level of probabilities. So given that the kind of not a whole lot of time, I'm just going to race through this little, this is goes into a little more detail about the nature of the interaction when we have, say, an excited atom and a bunch of ground state atoms that we can consider as potential absorbers. and how the formulation describes this interaction and effectively yields the Born rule. So we have what's called an offer wave, that's the emitted component, but the different absorbers can only receive and respond to components of that based on the momentum, directional momentum that is appropriate for them to receive that, and so on. So we got different components of this offer wave going to different absorbers. And then the part of the process that isn't represented in the Yang only standard way of looking at things is that each absorber actually does respond with a real, I say real field, a physically real field. It's got a complex form, but it's a physically real field. And the interaction of the offer wave component and this confirmation wave component gives rise to a set of incipient transactions. So clearly, if you have only one photon to give away, that one photon cannot go to all these responding absorbers. So there has to be some kind of a collapse. It's a non-unitary process. And this is how we get sort of a collapse happening. And just a little bit more detail on the relation there with the offer and the confirmation. And formally, the interaction of the offer and confirmation components are described by their outer product. So what we get is for each of them a projection operator corresponding to the property that may or may not be actualized, and this coefficient which you'll recognize as the Born rule. So this process naturally yields a physical basis for the Born rule. Now here I've just said, okay, suppose the one for absorber B gets actualized. Again, you can think of this as spontaneous symmetry breaking. So that sort of thing. Sometimes people are uneasy because they feel like we haven't said, well, why do you get this one instead of that one? But of course, we have situations like that elsewhere in physics with the Higgs boson, where we have an infinite number of vacuum states, and we say, well, one is chosen through spontaneous symmetry breaking. So some people have supposed that perhaps volition comes in at this point. So in any case, the theory itself will not tell you. Clearly, the theory itself is fundamentally indeterministic. But in this picture, we do get those Born probabilities coming right out. And another way to see this is that it describes von Neumann's process one, what he called the process one measurement transition, that it's non-unitary. And so we gain in this picture an account of this von Neumann's process one without having to say that measurement occurs in based on consciousness or a conscious observer, where we're going to obviously have trouble defining what counts as a conscious observer. So arguably with Yin back in the picture, we can clap and shake hands and get measurement outcomes. Okay, so now just some considerations, general considerations on this slide, a lot of words, which I'll just summarize by saying that this theory, the direct action theory, it includes formally and quantitatively in the theory, this Yin component. And it's kind of a useful exercise, I think, to take that seriously and to consider that, in other areas of interaction, you can't just give something away without somebody receiving it. You can't sell your home without a buyer. Worth noting that Wheeler actually returned to this theory in 2003 and began to advocate it as a way forward for quantum gravity. And just as a side note, we could maybe point to cultural reasons why absorption and reception don't seem to be seen or noticed or taken into account. There's this famous study by Emily Martin, an anthropologist who just looked at the literature in reproductive biology and noticed how what she called a romance, that science has constructed a romance based on stereotypical male and female roles. And that actually when people started looking into the process of fertilization, here we have an electron micrograph of the process in which you can clearly see the egg being active and doing various things to help the sperm find the egg and then to engulf a sperm that does get to the egg and preventing all the other ones from entering. So it's actually very active and crucial in the reproductive process. So just to mention that I've been extending the transactional picture into the relativistic domain, so you can provide in this formulation a quantitative account of what's termed absorber response in the non-relativistic theory, including the circumstances of its occurrence. Now, it is indeterministic, it's governed by decay rates essentially, but you can quantify under what circumstances this kind of interaction will occur. So in other words, one can no longer say, well, absorbers are primitive or absorber response is primitive, because it really isn't, it's defined in the theory. Now let's see, I'm going to start to wrap up with some ontological considerations. Now, these are essentially optional. To me, they are, I mean, for instance, one could consider the direct action theory approach and the transactional picture as a way to make progress in understanding the process of measurement and so on, without necessarily buying into, my suggestions here. Although I do think they're natural. I think they're hard to escape, essentially. That once we allow the idea that at a fundamental level, we have these yin type interactions are going on, and they're non-local. So we do have to let go of all of these sort of locality, unilateral local field propagation kinds of assumptions that we bring into our studies. But also I'd like to reevaluate the usual idea that space-time is sort of a container for everything real, and propose that in fact quantum entities do not live in space-time. So just to review our usual Western block world concept of space-time, most physicists do think that that space-time is like a block, and they argue, they claim that relativity requires that. It actually doesn't, but that's the general kind of default view. So it's thought that future events are real in the same way that past events are, and that we're sort of hanging out at now. It's generally assumed that we're moving through this block where that's basically primitive. It's kind of assumed. And then you can ask, well, why do we move through and like a rock doesn't? And so, or maybe it does, but how does it know it's moving through? So we get into some kind of strange, issues with that usually aren't kind of addressed. So it's thought we thought that we face the future with the past behind us. And this just kind of sums up the ontology of that I think is suggested by this picture, that in fact we need to take into account that is a system of correlated quantum systems in general that are not separable, say entangled quantum system, is really described by configuration space relating to the n degrees of freedom that are involved. And that's not a space-time domain. It has many, there's also the complexity, of course, of the wave functions. So if we want to be realist about quantum systems and we want to be realist about the theory that describes them, that I think it's useful to acknowledge another aspect of reality that in a paper with two other colleagues, we've called res potentia, and that the more space-time kinds of phenomenal level, which I'll get to a little bit further on, can be thought of as res extensa in the Cartesian sense. So the idea is that in fact the measurement process yields space-time events, and that they are emergent from this quantum level. So you can think of it that way, that the space-time theater really is kind of a theater. It's just the tip of the iceberg, and that we can be realist about quantum theory and suggest that it does describe a sub-empirical level, if you will, a level that is not tangible in the usual sense. We cannot detect it with our usual senses, but our theory, our very successful theory of quantum mechanics, is pointing to its existence. So something to consider. And in this picture, we're just kind of reviewing the idea that when you get a transaction, when you have an actualized transaction, what you're doing is essentially giving rise to an emission event, an absorption event, and the connection between them, which is the transferred photon. And this has a sort of a temporal arrow to it naturally. And there are more reasons than just this, but part of the understanding of this arrow is that the emission event must always precede the absorption event. So we get an emergent directed space-time from these actualized transactions. And I'm going to kind of rush to conclude here a little bit and skip over that, but just that we do get an ontological arrow of time. So the picture is more that of kind of a weaving of the fabric of space-time, which is simply a structured set of events that are the measurement outcomes. And interestingly, this picture has a lot of resonance with an indigenous group of people called the Aymara, whose language actually reflects their understanding that they are facing the past rather than facing the future. So that's kind of, I find that very interesting. And other unconventional views were held by Hans Reichenbach, who said the flow of time is a real becoming in which potentiality is transformed into actuality. And that's really exactly what I'm describing here. Rudolf Haag, who came up with Haag's theorem for describing the inconsistencies of quantum field theory, also noted this almost volitional aspect to the actualization of an outcome that he talked about as decisions in nature, comprising the transition of possibilities to fact. So, you know, I'm pointing to these kinds of insights I'm thinking and suggesting that we need to take them seriously. So as an additional dividend, we get from this picture what Richard David called unexpected explanatory closure. And Sabina Hassenfelder also mentioned this in her talk earlier last month, and where you get the unanticipated connection, sorry for the typo, between the formerly unrelated. So what we're getting here, I'm arguing, is that we're getting remediation of problems that were seemingly unrelated. We've got a way to define measurement and explain how we get outcomes. And we actually also get a resolution to this problem pointed to by Haag's theorem, because if we get rid of this conceptual oscillator field as a mechanical system, then we actually get rid of these inconsistencies and infinities. And I have a reference for that if anyone's interested. We get rid of the apparent incompatibility of quantum theory with general relativity. And we also get genuine irreversibility at the micro level, which can undergird the second law of thermodynamics. So just kind of briefly zooming through I think that clock might be a bit fast. Yes. Good. Okay, oh good, okay. So in this problem about the quantum field theory divergences, in the direct action theory, these are only force. So these divergences, assuming there's no natural cutoff, which there might be because in this picture, there's really a discreteness underlying the metaphysics. There's more of a discreteness and there's no assumed continuum of either conserved quantities or space-time. But suppose we grant that these might end up being infinities. These self-action infinities involve only that basic time symmetric propagator with the off-shell virtual photon quality. So there's no energy involved. It's sort of a force-only infinity. And we all know that you can adjust the zero of your potential energy. And so that's becomes not a problem. And also the idea of, oh dear, we have, 0 point energies that must be infinite because we have arbitrarily large, numbers of these infinities corresponding to different possible energy states. Well, we get rid of those with our getting rid of the independent set of oscillators. And we can actually understand the 0 point energy as simply the radiation reaction that occurs in a single transaction. And I have a reference on that if people are curious about how that could work. So the problem of the quantum field theory divergences gets kind of remedied. And then we have the concern about quantum theory's compatibility with relativity. Well, if we grant that general relativity is describing this emergent space-time manifold, but not the quantum level of possibility. So the issue of getting a metric, a well-defined metric, is kind of evaporates because we don't expect a metric to apply to the level of quantum, to the quantum substratum, since that is not the space-time construct. So the space-time construct becomes well-defined in terms of events that correspond to measurement results. And then general relativity describes the structure of that emergent set of events. Okay, so, and just noting here that it's interesting to observe that even in standard general relativity, the sources of the field, strictly speaking, cannot be in the field. So when you see, I wanted to do a picture of this, but I forgot. When you see the little kind of curved mattress pictures with the little masses hovering uncertainly above them, it's worth noting that those matter sources of the curvature are not in the field that is characterized by the curvature. So they are sources of the field. And where is the source? It's the quantum substratum. So space-time is basically curving into the quantum substratum. So that's just something fun to think about. May not be true, but something to think about. And then this other problem, we clearly get an irreversible process in this measurement, this non-unitary measurement. So this gives us a microscopic grounding for the second law, and I have a reference on that. It's given here. Okay, so kind of summing up here, that I would suggest quantum theory is trying to tell us that reality is bigger than we thought. So we have the classical level, which is our level of experience that tempts us to extend this kind of experience to the entire expanse of reality, and that has led to these discomforts with the non-locality and entanglement and non-local correlations and so on. But again, that's just the phenomenal level, according to this view, characterized by res extensa. And it has these kinds of properties. These are the properties that Bohr insisted on as conditions for reality. So what I'm suggesting is, well, no, we don't, there's no reason we need to do that. We can understand quantum theory as referring to an aspect of the world that is not like the usual macroscopic domain that we are used to. And one thing you can do if you're adventurous is identify this classical level with the Kantian phenomenal level. And you can identify the quantum level with the Kantian noumenal level. That's very controversial. I reckon Kant scholars may want to throw tomatoes at me for saying that, but since we only have apples, you'll have to settle for apples. But anyway, I just throw that out there. I think it's an intriguing thought that in some ways does address Kant's definition of the noumenal realm, and that they are possibilities. They do not exist in space-time. They're empirically inaccessible, so they can't be known the way Kant wanted things to be known, which is by sensory confirmation and so on. So in conclusion, I've argued that multiple problems and challenges in physics are solved by applying the direct action theory to the fields underlying quantum theory, and that quantum theory could be taken as describing a subempirical domain of res potentia. Non-locality is an ontological feature of that domain, and all material systems, by which I mean systems with non-vanishing rest mass, actually exist in this quantum substrate. They undergo transactions which transfer real photons and thereby create actualized events and their connections, which constitutes the domain of res extensa, in other words, space-time. Locality does apply, but only to this emergent structured set of events. And that gravitation is the structure of those, the emerging set of events. And this, you can develop this in connection with a form of entropic gravity. I'm working on this with a colleague, Andreas Schlatter, who's already written some interesting papers about this approach. Okay, so concluding in there, and just a shameless plug for my second edition, which the first edition came out in 2012. It was called The Transactional Interpretation of Quantum Mechanics, the Reality of Possibility. The second edition has a different subtitle, although I still argue that we do have quantum theory referring to real possibility. The subtitle of this one is A Relativistic Treatment, since it's making clear that this is explicating the fully relativistic aspects of the theory. So a few references if anyone wants anything, and thank you very much for coming.
We'll take a 2-minute break and then we'll reconvene for questions.
Oh, it's good.
No, we always.
Oh, yeah, yeah, I see.
If possible, it would be great if you could keep the questions that you get from people so that the online audience.
Gotcha, I will do
They
my
always have
best.
trouble hearing.
Yeah, I'll do my best.
Okay, yeah.
Okay, thanks.
It's kind of a hard thing to remember in the moment, but.
I will try to do that. Maybe I
Yeah.
should try to mute this, scribble something down. Still a little piece of paper.
Oh, okay.
Yeah, everything. Yeah. So this is a talk you've given before, or is this new for us? Or? Oh, you're probably, yes, you're probably being streamed. So
If I keep my hand on the mute button, does that work?
I don't know. Why don't you just assume you're being streamed and answer accordingly?
Okay. Well, I've given, I mean, a lot of the slides are from talks I've given before. But this is more tailored for an audience that knows more, probably knows more technically. So I focus more on some of the technical aspects. I have other things where I talk more about the cultural, implications and that kind of thing. So I've actually given a couple of talks for the Perry Center, which is an interesting interdisciplinary group that was founded by David Peat, a colleague of Bowman Hiley of David Peat, and it's run by his son and his daughter and a bunch of colleagues, and they are very interested in spiritual implications and societal implications and that sort of thing. So
all of this is the tip of an iceberg, and we're not seeing the whole iceberg, are we?
no,
Yeah.
in terms of what I presented or just
Your thoughts, the whole research.
Yeah, this was like just the cartoon version. I think it was just like I felt really kind of like I'm totally skimming over the surface here, but there are a lot of very well-developed, I mean, more fully developed explications of this process and what's going on. And it's in preprints on the archive server right now, so. But most of that is going to be in the second edition. Just put it out there.
All right, let's get started. Before we have the first question, let me remind you for those online, if you have a question, please write down your name on the Q&A box, and I'll bring you live so that you can ask a question directly. John, the floor is yours.
Okay.
Okay, so thanks very much. You covered so much ground, it's hard to know what to ask about. What I want to try and do, though, is get a better grasp on how you're dealing with what's called the measurement problem. Right now, it happened in the slide where you talked about the offer and confirmation. And I followed all the way through to a point where something happened. Right? And I want to take you through to the point and then ask what happened. Right? So here you have a central emitter, which is making the offer. I'm not quite sure. Then you had three possible detectors. I'm assuming it's possible for us to imagine them laid out sort of symmetrically surrounding it. So we have the emitter sends out a wave that goes out symmetrically. Now, if this were, for example, a gamma decay, right, the gamma wave would go out symmetrically, and then only one of the three detectors would fire. But the quantum mechanical story would be that you have the wave going out. It's the operator wave going out, and then it interacts with all three of them, and we go into a superposition of detector A fired, detector B fired, detector C fired. Right, we're in that superposition. But then the critical moment was you said, but there's only one photon, right? Therefore, only one of them can fire. And out comes the Born rule. Now, I'm assuming that there's a lot more in that sentence. There's only one photon, but that's the sentence that gives you either it gives you real collapse or the appearance of collapse or something. So how does that part work?
Okay, so so Professor Norton is asking for a little bit more detail on the measurement process itself. And what happens. I wonder if it's possible to get that slide back up. I don't know. Maybe I don't know. That might
Yeah, if
be.
you click share screen, you should be able to. Screen and select your PowerPoint.
I'm not sure. Not seeing it in the options to share, but.
Oh, let's see.
Okay, let the pros do it. Okay. So the key thing before I get to it is that there's no superposition. There's no superposition in the usual unitary sense once the you get absorber response. So that's not that breaks the linearity. I should have been more clear about that. So thank you for your question. At the stage of this this absorber response, unitary is broken already. And
so can you explain then how that happens? Because that's already the surprising bit. Quantum mechanics, we're told, is a linear theory.
Exactly.
So now you're telling me it's not a linear theory. What's happened?
Right. So in the direct action theory, quantum mechanics is not a purely linear theory. And so in order to understand the nonlinearity that happens, I need to go back to.
Just to jump ahead, is this the real refinement stuff where you have an asymmetry between the emitter and you have this big absorbing shell?
No, you don't particularly need an asymmetry. All you need is an emitting and absorbing situation that satisfies energy conservation. And to get these details, what you really need to do, the details of this are in the relativistic explication that that describes the interaction between emitters and absorbers. So that, let me just get my two different levels of, trying to find my two different levels of, okay. So this picture here shows the non-unitary process. So already here we've got, when we've got an absorber responding to an emitter, even if it's just one, suppose we only had one absorber, we would still have a non-unitary process.
That's not at all obvious. If I imagine the time direction flipped here, then I have a propagation into the past. I thought the whole trick with the wheel of Feynman theory was you have an asymmetry between the emitter and a large number of absorbers, and it's
that would be the classical theory. Yes, this is the fully quantum relativistic direct action theory. And the key here is that, I mean, in the classical theory, you don't have quantized energy. So you can dole out little bits of energy to all of and you have this light tight box condition and all of this stuff. That does not apply in that way to the quantum version of it.
So that was the remark about the photon.
Well, yes, that's a way in which it
sounded to me like
differs.
you were privileging a Fock space representation where you have a definite number of photons.
You don't actually have to have a definite number of photons in the direct action theory. In order to have absorber response, you need a situation in which energy conservation applies. And so the way that that's implemented is through the delivery of well-defined numbers of photons. And that doesn't mean you can't have what's called a coherent state. In the direct action theory, the coherent state really describes the absorber and emitter, the field sources being in an uncertain state as to when and how many photons they will emit. So you can have coherent states in the direct action theory. But, you know, as far as there may be discomfort with the idea of privileging a particular observable, although I'm not sure that is your concern. But, you know, if you look,
no, that would be.
that part of it.
I take it the same thing. Sorry, I'll just.
No, go ahead.
No, that's fine.
But
Sure.
You're talking about conserving energy. Are we conserving momentum as well?
Yes, we're
So
the
if we
conserved
have-
currents.
If we have an emitter that's emitting a spherically symmetric wave, and then it gets detected over here, so we now have a photon with a momentum going in a particular direction. That looks to me like a collapse because the
It
wave
is.
going out is in a superposition
That is a
of many momentum states. How does that? I mean,
so that is
that's
a
the thing. How
collapse,
does that-
but
how
but
does
the
that work?
wave going out now, at the relativistic level, what's required is remember what I said about yin and non-locality. At the subtle level, sources are always in touch with each other, loosely speaking, through the time symmetric propagator. At some point, they can mutually decide, if you pardon the anthropomorphic language, if the energy conservation can be satisfied. That is when you can have a situation that's called absorber response at the non-relativistic level. But it's really a mutual interaction that elevates the interaction to this non-unitary stage. And that, so in other words, it's really an unwarranted idealization to think that first there's this spherically expanding wave and then things respond. No, at the fully relativistic level, what looks like a spherically expanding wave is actually perhaps a vast number of emitter, absorber, incipient transactions. And once you've got that absorber, in other words, absorber response doesn't happen after the offer. It's a mutual non-unitary engagement that defines this proper mixed state that are a bunch of projection operators. So there's no superposition at that stage.
So, and this would be the case if we only had two detectors, say. So you've got
However many
so just two
detectors.
You've got what we would naively think of as the emitter. It's been talking in an atemporal way, as it were, with using advanced and retarded propagations with the two guys on either side. Everything I've said so far is completely symmetric. then something breaks the symmetry so that only one of them gets the energy or the momentum. And what's the thing that breaks the symmetry? Because everything I've said so far is symmetric over the two cases. I mean, they're talking with one another and they've decided.
Right. Well, one
you're the guy
asymmetry,
who's
there are
gonna get it
different
out.
aspects to this asymmetry. One is that there's an excited atom that has energy, has excess energy and is slightly unstable. And then the other two are presumably in their ground state. So there's an asymmetry there. That is what leads to the temporal asymmetry, because you can't absorb something that it doesn't exist. You have to have that energy. So that's the temporal asymmetry.
No
That
worries.
now, as far as the collapse, now again, you know, like the direct action theory will not give you a causal mechanical deterministic account of why or how one of the incipient transactions gets actualized. It will not do that. So this is where symmetry breaking enters, if you wish. Now, sometimes people think of that. Was it Hogg who talked about volition in nature, comprising a transition of possibilities to fact? We always have more possibilities than can be actualized in the space-time realm. And as far as the concern about, well, you know, you haven't explained why we get B instead of A, receiving it, that isn't really the measurement problem. The measurement problem is defining what a measurement is, where, and showing that the linearity is broken. Because there are like two steps to the von Neumann transition. There's the transition from a pure to a mixed state. And then, if you will, there's the second part where you get a reduction of that mixed state to one outcome. So that's where we are in this picture. And again, you know, you can point to the Higgs boson, you know, for the Higgs mechanism, in which we have a similar kind of many more solutions than can be realized in nature. And we don't really know, well, why is one of those realized?
So last attempt, I think I'm getting the picture now. So
Okay.
we have emitter in the middle, two absorbers on either side. So far, everything's described symmetrically. They're talking to each other through advanced and retarded propagations. How do we fill out the picture? One way we fill it out is that this absorber here reacts, right? And another way, second story completely, is that this absorber here reacts.
When you say react, do you mean confirms?
It gets excited. It gets excited.
Oh, receives the photon.
Yeah, it receives the photon.
Okay.
Exactly. Fine. The normal issue would then be, why can't we have the superposition of both of those?
Because we've broken the linear propagation when you got the absorber response. The actual physical situation then is described by a projection operator. So it's not a pure state anymore.
That sounds like a collapse postulate.
It's not a postulate because it's actually part of the theory.
Well,
I can
it
show you
sounds
that.
like this collapse posited by the theory. Why does it have to be a projection operator? Why can't you just have, we've gone into superposition? Why wouldn't that be allowed by the theory?
Well, it isn't, because I think if you look at the references, you'll see that the Feynman propagator actually does have this real and imaginary part, where the imaginary part does lead to a real non-unitary process in nature. So it's not just a postulate, it's describing an actual physical non-unitary process in nature. Yeah. But I'm happy to show you where it's laid out in detail, and then we can discuss more if you're not happy.
Thanks. Right.
Thank you for this fascinating talk. Two things. Since you made this risky reference to Kant, I would like to make some more risky references, namely, insofar as Western metaphysical traditions, let's say, are concerned, this notion of actualization and this idea that the manifest image of the world is a kind of actualization of something beyond, let's say, it goes back to Aristotle for sure. He articulates basically anything in terms of potential actual, and then to Plato, to Leibniz for sure, and Spinoza, and even you know, in medieval philosophy, everything is mixed with theology, but they also had this notion of creatio continua in Latin. So all these things are interesting, I would say, and to what extent this issue is worked out by you or your colleagues, and to what extent it's really significant. So this is one question, and kind of invitation for you to speculate a little bit more. And the second thing is the concept of agent, because you mentioned agent at the very beginning of your presentation when the issue of instrumentalism versus realism was discussed. And I wonder whether this notion of agent is assumed as given, and being an agent means it refers to whatever it is that performs the measurement or whatever, or is there a place for a thicker, let's say, notion of the agent, like a living creature, an evolving creature, a representational system, a computational system? You know, we can have very different concepts of the agent. So to what extent, the question I guess is, to what extent this is relevant, how we define the agent? Thank you.
Okay, so we have two questions. The first question is basically how specific do I want to get with the Kantian reference? And you know that it's just a suggestion at this point. I don't purport to be a Kant scholar in any way, shape, or form. I do just suggest, however, that the idea of the thing in itself, that's always been a challenge for Kant, in the sense that he wants to kind of connect to this noumenal world, but he doesn't have any way to do it. And because of the way he defines knowledge as inevitably filtered through human concepts and so on. So I'm kind of going out on a limb just in saying that our best theories can possibly point to aspects of reality that could be thought of as things in themselves, only, you know, maybe in the restricted sense that they are intangible. We can't know them in the phenomenal sense. So we can't know them in the phenomenal sense. Perhaps if we want to be realist about quantum theory, we could suggest that this is a way to gain knowledge that isn't phenomenal forms of knowledge. So it's, you know, it's a risky suggestion, and I don't claim to, you know, have a detailed justification of that. The second question was about agents, and I don't use that term myself because I find it to implicitly smuggle in instrumentalism, and I take quantum theory as describing the world. So I don't need to talk about what counts as an agent. In general, though, I feel as though in the literature, there are different levels of attempting to specify what they mean by an agent. Typically, they will say like a human experimental, or they will talk about the experimenter's mind or brain as playing the role of agent. But again, for me, it begs the question, you know, is a cat an agent? You know, is an amoeba an agent? So I feel it's kind of a weak point of the discussion. So our moderator's gone.
So I had a quick question for you. Is that a question? Yeah.
Well, you can go. I don't mind.
I'll go first.
You're very brave because you're saying you can bring quantum mechanics and general relativity together. So do you want to say a bit more about that? I mean, the metric field, general relativity is just going to be treated like another, you know, advanced and retarded propagation. Where does the the time evolution operator is, you know, by h by d dt. What's the t? Because that normally comes out of the metric. Just can you say just a bit more, just
how do we deal with I guess maybe I take your question to be, how do we deal with the notion of time in relativity, if in this picture, we only have discrete events and so on. It's the time evolution, you can define say a proper time. You can still define the concept of proper time. I discussed this also in my second edition, that field sources, fermionic field sources through their half integral spin have a kind of internal clock. And that's a perfectly valid temporal reference. All we have to be careful simply not to make that a preferred time and simply take it as a proper time applying to that object. And in fact, what we call space-time, we think of inertial frames generally as being things that are in space-time, but they're not. They're, according to this view, they are internal references only. So if you could think of yourself as an atom or electron, say, in this quantum substratum, your evolution, your unitary evolution, is still perfectly well described by the Schrodinger equation, if you like, where the relevant time parameter then is your proper time. So you get all of that. The unitary evolution doesn't go away in any way. It's simply that if you're going to apply a metric, the metric applies to the actualized events and their relationships.
So in other words, if I have a fermion, it's the internal rotation of the phase factor that is time. If I have 23 fermions that are non-interacting, I take it they're all coordinated in their phase factors, and that coordination would be the surrogate for time. Is that, am I getting the picture, or is that not it?
Time would be local. Time would be, I believe you said something that I believe that you noted that the concept of now is purely local. So I'm not sure if that's relevant to your question here,
Not
but
really. No, I'm just trying to figure out how this.
you have to always specify which, well, you simply have to specify which frame you're talking about. I don't know what the relationship is of those other electrons you're talking about. So
let's say they're all at rest.
they're all at rest relative to one another, then they'd be in a common inertial frame.
Right.
And again, you can talk about inertial frames. They're not part of the space-time construct. They're references by which you can tag events. So in other words, the irony here is that space-time is not made up of space or time. It's made up of events and their connections, which are the null intervals. And Einstein did say this. Einstein said that space-time is the set of events. That's the metric field, set of events. It's not space. Space and time are both in non-invariant concepts anyway. So what the space-time construct is composed of events and their connections. So that's consistent, at least, with how Einstein understood this theory.
Right. I think we probably should stop now. Thank you, Ruth.
Okay.
There's more gift from the center.
Thank you.
And see you on Friday. Thank you.